Welcome to today's video. Today we're going to talk about smooth maps. We're going to talk about pullbacks and push forwards, and we're going to talk about diffeomorphisms. Let's have here two manifolds, M and M prime. I don't know, flowers and kittens, for example. And these two manifolds, I create a map, something that maps points of the manifold M to points on the manifold M prime. For example, a point P in the manifold M is mapped to a point P prime in the manifold M prime. Sure. Now we can say, okay, so this is kind of a map that takes me from one manifold to another. How can I call it smooth? What does it mean for that to be smooth? What does it mean from a map from flowers to kittens to be smooth? Well, luckily, we have a structure of differentiable manifold that we can use to define smoothness. We use the atlases that we have in both manifolds that translate to M to our N and M prime to our M, right? And through that, I know that the point P can be translated via these homeomorphisms to the coordinates of the point P in this particular assignment of coordinates that phi makes, and that gives me P mu. Likewise, P prime can be mapped to Rm through phi beta prime that I call here. So phi beta prime assigns a set of coordinates to the point P prime mu. Okay. Now, of course, I can do the composition that I have here. So start from Rn, start from P mu, the coordinates of the point P, and then apply alpha minus 1, then I go here, then apply phi, then I go here, and then apply phi beta prime, and then I go here, right? So the composition map is truly a map from Rn to Rm, and in that sense, this map, I can talk about smoothness because multivariable calculus is what I know how to do. Rn to Rm, I know exactly what does it mean to be smooth, all right? So infinitely differentiable map, it will be, okay? And infinitely the composition of phi with these two homeomorphisms will be the map from Rn to Rm will be an infinitely differentiable map, and that's what we call a smooth map. All right, now that we've established, remember, we have a smooth map, phi, that moves points from P, from the world of flowers, to the domain of kittens, point P prime. Now that smooth map goes in this direction, but the interesting thing is that the existence of this map allows me to create a map, induces a map between the space of functions on M and on M prime. What are the functions? Remember, the functions take points in M to R. This would be a function, and on M, and the functions F prime, if you want, take points in M prime to R. Now, look at that. Imagine that I want to apply the function F prime. The function F prime is great. Takes the kittens to greatness. I really want to apply it to flowers. But you can't. What do you mean? Well, you can't. Those are kittens. Those are flowers. You can't really do the same things that you do to kittens to flowers. Oh, but maybe I can, because I have a map phi. What do you mean? Yes, the map phi takes a point in the flower manifold, M, and pulls it to the kitten domain, and once in the kitten domain, I hit it with F prime and get here. So if I define the pullback as a map that does the following, first, takes a point P, takes the point P to M prime through the smooth map, and then I apply F prime, and I say that that thing is a function of M going from M to the real. This is precisely what we call it the pullback, because it's pulling the function F prime back to the manifold M. All right, let's continue with the video. So I define a function F as the pullback, which is the composition of the smooth map, and F prime. You see what it happens? So it takes me from the point P to what would be the point applying the function F prime after having been taken through phi to the point P prime. So I do this, that, and the resulting function is this one. This is literally pulling, that's why it's called pullback. I want to pull P back here and then apply the function, hit it with the function. And this is the definition of the pullback. Important. Maybe you want to do the opposite. Oh, now that I can do that, I know that there are some flower functions that would be nice to apply to kittens. Can I take this P prime there and then from there to here? Well, not necessarily, no, because we haven't said anything about phi minus 1. For that, you need first to go back in this direction using phi minus 1 and then use a function here to get to the reals. But phi minus 1 may not exist. We have no guarantee that this exists yet. All right, next step. Despite of the fact that we cannot have a push forward for the space of functions, I cannot define functions on M prime that take me to the reals through going to M, I can do it with vectors. The existence of the smooth map bar phi makes me able to define a map that I call bar phi sub asterisk which we will call the push forwards, between the tangent spaces TPM and TP prime M prime. So what is this? These are the vector space, the space of vectors of the tangent space at the point P in the manifold M, and this one is the space of vectors at the point P prime, which remember P prime is the image of P under the smooth map phi. I'm going to associate a vector that is tangent to M prime. I'm going to define it through the vectors that are tangent to P in the manifold M. How do I do it? Well, given a vector V in the manifold M, I'm going to associate it with a vector phi star V in the tangent vector space to M prime at P prime. How do I do it? Well, how do I define a vector? Remember, vectors are defined by their actions on functions, okay? So I just need to tell you how it will act on functions f prime of the manifold M prime. If we want to visualize the problem, we can, it becomes more difficult as we go up in structures, say that this is P, right? And this thing, let's say like that, represents the tangent vector space to P at this point. And I have, let me just write with an arrow here, a vector V. And then I have, this is in M. And then I have here a point P prime, right? And this P prime is the image of P through bar phi. And I also have a tangent vector space here. This tangent vector space is T, P prime, M prime. This is M prime, right? This is T, P, M. And here I have another vector. And that vector I'm going to call the push forward of the vector V. All right? And how do I define this vector? Well, I know what this vector does. This vector takes the directional derivative in this direction of functions on the manifold, functions that take me to the reals. So these vectors, and you need to tell me how this vector takes functions f prime that go from M prime to the reals to define this vector here. And how do I do it? Well, through the bar phi map. So basically it's telling me the following. All right, how does it act on the function f prime? So I have a function f prime, right, going to the reals. That's the function, and it goes to the reals. So how does this vector act on this function? Well, first of all, take the function, apply the pullback. Now, the pullback of the function f prime takes the function to a function on M. And now that it's a function on M, I know how to hit it with the vector V that is on M. So basically it's telling me, first take your function, use the pullback to pull it back to M, and then hit it with the vector V, because the vector V applies to functions that goes from M to the reals. And then that action is exactly how I define the action of the vector push forward V on functions f prime that takes me from M prime to the reals. Hope that this is clear. Remember, I can define, so I don't know a way to act with vectors in M prime on functions on M, because they're just different worlds. They're just potatoes and flowers, you know, like something that is not related. But I know that I can translate the function f prime with the pullback into a function on M. And then once I'm in M, I can hit it with a vector V. So I define a new vector in the tangent space P prime in M prime, such that the action on functions f prime will be first pull it back to M, then hit it with the vector V. And that defines a vector in here, in M prime. Again, same as before, we can only bring vectors that are in M, push them forward to M prime. But we cannot pull back vectors of M prime to M, because we don't know if bar phi has an inverse, and therefore we don't know if bar phi star has an inverse. But you see what we can do? We can actually zigzag our way. We can pull back functions from M to M prime, and then we can push forward vectors from M prime, from the tangent vectors to M prime at a point, to M. Now, what do you think we can do? We can also pull back now one forms from M prime to M. Let's see how we do it. As promised, the math phi induces a pullback between the cotangent vector spaces T star P prime M prime. So the one forms at a point P prime in M prime, and the one forms at a point P in M, according to the following rule. Given a one form in omega prime in the cotangent space to P prime in M prime, then I'm going to define a one form at a point P in M, a different one form that I call the pullback omega prime, such that its action on vectors of the tangent vector space at the point P in M, so you see it truly acts on M, is defined by the following. How do you define a one form? Well, you have to tell me how it acts on vectors. Remember what a one form is. It's a linear functional that eats vectors and spits out scalars. So tell me how this form acts on vectors. This V is in vectors. V, remember, is in TPM, right? So how does this one form act on vectors at the point P? Well, I'll tell you how. Go to the other manifold, get the vector V, and now push it forward. Remember, vector V we can push forward to M prime, as we just did. And once you're there, then act with omega prime. You see, I have the vector V, remember that we had it here, M, and we have the point P, and we have the vector V, right, in the tangent space, if you want. And then we have here M prime, then again, the point P prime, right? And then the vector here that was phi star V, right? That's the vector. And this phi star V, we have the map between the points phi, and we have, we've actually pushed forward the vector V here, and it became this one. So what I'm telling you is that, okay, you have the omega prime living here, get the vector V, push it forward here, and let me hit it. You see, omega prime doesn't want to go, cannot go all over there, but I said, no, push it forward here, and let me hit it. So push forward the vector V here, and let me hit it, because I know how to hit vectors that live in here. So I hit with the one form, omega prime, the push forward version of the vector V, which is a vector in the tangent space to the point P prime, and that defines the action of how this one form, now this defines in itself a one form here. It's like, a one form here that, oh, you want to do that to that vector? I can do it myself. Punch! See what I mean? So this one form hits vectors V's, and that's exactly the same as the form omega prime does when it hits the push forward version of the vector V. And that's a definition. Now, from this discussion, you can probably tell that we can define pullbacks for covariant tensors, and we can define push forwards for contravariant tensors. So it's like zigzagging away in the chain of covariance. All right. Let's prove a little identity to just get acquainted with how to use these things, because I know they can be a little abstract. Let me just recap what we've learned so far and use it to prove something. All right, I compiled here three identities that we had. The first one is just the definition of the differential of a function, which is defined as the one form that acting on vectors returns the action of the vector on the function. That's from the beginning of the block of differential geometry. I got here the definition of the push forward of a vector, and here the thing that we just saw, which is the definition of the pullback of a one form. Now with these three things, we can prove the following identity, which is, this could be an easy exercise. I mean, I call it easy, but I don't mean it in a demeaning kind of way. I know that it's easy only if you're familiar with this thing. You've been doing it for a while. For many of you, this is kind of new abstract math, so I understand that it's not that easy. Anyway, it's an exercise on the lower tier of difficulty in terms of what the exercise that you can give with this abstract math. So let's do it in detail. I want you to prove that this, which is that the differential commutes with the pullback. So this is the pullback of the differential of f prime at the point P, and I want you to prove that this is equal to the differential of the pullback of f prime at the point bar phi P. To prove it, let's analyze this one form. To analyze this one form, let's act on an arbitrary vector. So I can act with this one form. Remember, this one form is a form in the tangent, in cotangent vector space to P in M, right? So this thing, df prime, let me act on a vector V. This at the point P, right? What is that? Well, the nice thing is I have the definition of the pullback of a one form here. Now the one form I'm dealing with here is df prime, so I substitute, and I get here, this is gonna be df prime acting on the push forward version of the vector V. So you see we've moved to the other, this is a real number, but we expressed it now in terms of quantities in the other manifold. So we have now here P prime. Remember, P prime is the map, the image of the point P under the smooth map phi. Okay, wonderful. Now what I use is the definition of the differential of a function. The differential of a function acts on a vector by getting me the directional derivative of the function in the direction of the vector. So the action of the vector on the function. So I apply that, and I get the vector here is the push forward version of the vector V acting on the function f prime. And if you want, this is at the point P prime. All right. Now, what next? Well, this is, let me just write it like this, okay? This is a vector acting on the function. The nice thing is that I can use now the definition of the push-forward map for the vector. This is exactly equal to the vector v now at the point P, acting on the pullback version of the function f prime. All right. And now what I can do is back to the action of the differential of a function on a vector. So I know that this is the directional derivative of the pullback version of f prime, right? But this is taken by the vector. That I know that this is equal to the differential of the function inside. So the differential of bar phi f prime acting on the vector v at the point P. All right. And now, because this is true for any vector v, we know that this thing has to be equal to this thing, and we have proven what we wanted. It's an easy proof. Again, it's abstract math. For those of you who have taken pure math courses, this is a simple proof, but by no means is simple, I understand, when this is the first time that you face this kind of abstract math. But I hope you see the power of this abstract math when we talked about calculus, integrals, and generalizing the things that you kind of knew how to use, but looking in the eyes to those concepts. All right, let's move to diffeomorphisms. Okay, a map from a manifold to another manifold M prime is a diffeomorphism if it's a smooth map, and then it's got an inverse, and the inverse is also smooth. This is nice because the existence of this invertible map that is smooth allows me to define pullbacks and push forwards between all the objects that I want, both in manifold M and M prime. Now, let's focus on the case that is interesting to us, which is diffeomorphisms from the manifold to itself. Let's think of the following. Imagine that I have a curve, right, on the manifold. I have a point P that I call the curve at 0. I parameterize the curve in terms of a parameter S, think of a time parameter or whatever. And then at every point, I have a vector field x, that is the tangent vector field, right? At this point, it would be like that. At this point, it would be like that. Is the tangent vector field represented like that? The tangent vector field to the curve in the manifold. So it's a vector field. I can define a map that takes this point along the curve. And for a small, a local area around the point P, I can define a map, let me call it S, like that, a bar phi S that takes the point P and transports the point along the curve. All right? How do you define this map? So it's very easy. It's related to the tangent vector that I have here. Because basically this map is telling me, take S steps in the direction of the tangent vector. So follow the tangent vectors, still take S steps following the tangent vector. So if I give you the tangent vectors to a curve, right, and I tell you to follow it, you're gonna be able, using this map, that the local diffeomorphism, the map that transports the point along the curve, just following the tangent vector is gonna eventually draw your curve, right? Okay, so I can define these diffeomorphisms that transports locally the point P along the curve. And also, I know that if I transport, let's see, S plus T, right, to the point P, well, it's gonna take me to gamma S plus T. So certainly, and this thing is like, okay, move S steps first, and then move T steps after, right? So from P, go T steps, and then S steps, right? But what I said would be kind of the opposite. So T here and S, doesn't really matter for this example, but is what I said. So this map takes S steps from P, and then T steps from what it results, following the tangent vector to the curve. So this is certainly the same as getting S plus T on the point P. So this operation from a group, and this group is what we call the local flow of the vector x. Remember, the vector field x is generating the curve. You see what I mean? So I told you what the vector field is at every point, and then you know how to join the dots. The vector x generates this group of transformations. So this notion of tangent vectors to a curve generating a flow that transports me around the curve is very important in physics, because physics is talked about mechanics, is talked about through these local flows integrated. Remember that vector fields are a Lie algebra. And you can tell how, you remember through the exponential map from the Lie algebra element of the group. Element of the algebra, element of the group. So you see the relationship. So when we talk about time evolution or translations or any transformation like that, we are following the local flow of a vector field, and that vector field is the element of the algebra that when through the exponential map generates the operation of the group. So this is the differential geometry way of writing this. This is the kind of thing that you've been doing in mechanics, that you've been doing in quantum mechanics, that we did in special relativity without specifying. Now you have the abstract tools to handle it. All right, one more notion for this video, which is the notion of Lie derivative. Okay, let's learn about the Lie derivative. Not lie derivative, Lie derivative. Derivatives don't lie. Okay, so we have a diffeomorphism that goes from the manifold to itself, right? So something like that. A diffeomorphism takes me from the point P to the point bar phi P, okay? And then I have, of course, because it's a diffeomorphism, then I can define pullbacks between all the tensor spaces, the tangent vector space, cotangent vector space, the space of two tensors, etc., from the point bar phi P to the point P. Because remember, if we have an inverse, we can define pullbacks always. And now we can wonder, how do I compare? Imagine that I have a tensor field, say it's a vector field. For example, the electric field in this room. I want to compare the electric field here with the electric field here. How do I compare them? Well, you can't, because the tensor field evaluated here belongs, it's actually an element of the, if it's a vector field, for example, of the tangent vector space to the manifold here. And this one is an element of the tangent vector space to the manifold here. They're different spaces. It's apples and pears. You cannot compare them. Well, if I have a pullback, I mean, again, you may not have the luxury that the two spaces are similar at all. The tangent vector space here and here may be different, right? Well, you kind of have a way to compare them, which is using the pullbacks. So I can get the tensor field in the corner of the room, I can pull it back to where I am, right? And then I can subtract it from the tensor field where I am. So that allows me to compare the tensor field values, if you want, the values of the tensor field at different points. Okay. Now, in particular, let's consider that this diffeomorphism phi is generated by is the local flow of some tangent vector, right? Or some vector field V. So I have a curve, right? And this is the vector field V that I wrote here. And this curve is generated by taking small steps in the direction of the tangent vector, right? And this is the diffeomorphism that generates that curve, right? That gives me the flow of that vector, that draws the curve. Okay, then we define the Lie derivative of a tensor T along we would say along the vector V at the point P, but along the curve generated by the vector V at the point P, if you want, as follows. So Lie derivative of the point P is, okay, take the tensor at a point that is t steps away from P. So I take t steps, here, the tensor here. Then pull it back to the point P and subtract the value of the tensor P. And then divide by the distance that you walked. And then take the limit of that distance going to 0. So this is a generalization of the notion of derivative that you know, that is, okay, yeah, move a little bit and subtract the value, move a little bit, evaluate and subtract the value before you move, divide by distance, take the limit when it goes to 0. So this is the definition of the derivative that uses and relies on pullbacks. Of course, it depends on, that's why you have a V here, it depends on the vector field. It depends on the curve, in what way you come, one way you pull it back, the tensor at the point bar phi P, which way do you pull it back? That depends on the curve that you follow to pull it back. Of course, then that means that depends on the tangent vector space. All right. Now, this is a derivative, very easy to prove that, well, it's obviously linear. It's also satisfies Leibniz rule with respect to the tensor product. So it's definitely a derivation. All right. So I hope that the conceptual notion of the Lie derivative is understood. It's again, take a differential step here, pull back the tensor field where it was, where I started, and compare with the tensor field where I started. And take the limit of that distance that you walk to be very small. That's the notion, the conceptual notion. So it's truly a variation of a tensor field as I move through curves, right? How does the electric field in my room varies as I move in this trajectory? That is what the Lie derivative is informing me about. Okay. Now, this Lie derivative, how do I compute it? Keep in mind that the Lie derivative preserves the tensor nature of the tensor. If you have a tensor that is 3 times covariant and 4 times contravariant, the Lie derivative will still be 3 times covariance and 4 times contravariant. So it doesn't change the nature, covariant and contravariant nature of the tensor. Let's learn how to compute Lie derivatives. All right, we're going to compute the lead derivative of different things, fill the gap with whatever you want, along the curve generated by the vector field V. So V is a vector field that tells me how to take my steps locally to draw the curve, right? So, first, the lead derivative of a function, of a scalar field. Okay, well that's easy. From the definition that we have, is the function here, pull it back here, divide by the distance, that is the directional derivative in the direction of the curve. And we know that the directional derivative in the direction of the curve of a function f, it's given by the action of the tangent vector to the curve on the function. That's one of the first things we learned in differential geometry in the video about vectors. Wonderful, so we have it already. Look at that. The lead derivative of a function in the direction of v is just the directional derivative of the function in the direction of the vector. That is, the action of the vector on the function. Very nice. We can certainly ask what's the value of this lead derivative in a coordinate basis. So if I have a coordinate basis, then I know that this is just, the directional derivative of the function, as we know. Technically, you would write a bar here, but we are not doing it anymore, not to lighten a little bit the notation, but we understand what we're doing. You take the partial derivative of the function and contract it with the vector, with the components of the vector v, right? So this is literally the equivalent to what you wrote, although we don't have an inner product yet, but this is kind of the same, right? When you wrote that in calculus for the directional derivative of the function. All right, wonderful. So now let's see what is the lead derivative of a vector field. All right, to compute the lead derivative of a vector field w in the direction of v, we're going to use a little trick. I'm going to compute the lead derivative of the vector field w acting on the function f. Why is that? Because this is a function in itself, remember? And we know what it is. This thing, it's equal to two things at the same time. Okay, let's write it here. On the one hand, I get that this is going to be, I'm going to write two things here. This is going to be, of course, using Leibniz rule, this is going to be, remember that w is a linear operator on f. So I can use Leibniz rule and get the following. This is going to be the lead derivative of w acting on f plus the w acting on the lead derivative of f. Right? That's on the one hand. On the other hand, I know that this is the lead derivative with respect to v, or I can do this action inside with respect to v of, this is going to be w mu partial mu in a coordinate basis. I just pick a coordinate basis to do it. This is going to be partial mu f. All right. Wonderful. So that is kind of nice because I can equate these two things, right? If I equate these two things, this is very interesting because this is the lead derivative of a function. This thing is a function itself. It's a scalar, no indices, right? And this thing is also the lead derivative of a function that I know how to compute. Now, in this equality, I can isolate for this thing, which is what I want. Everything else I know to compute. This is the lead derivative of a function. This is the lead derivative of a function. All that is left to compute is the lead derivative of a vector that I don't know how to compute. But let's put it on the left. So I put lead derivative with respect to v of the vector w acting on f. This thing has to be equal to the lead derivative with respect to v of w mu partial mu f minus w acting on the lead derivative of f. Okay, but then this is kind of easy because I know that this parenthesis is going to be, let's write it here, v mu partial mu f, and then you act, this is a function in itself, and then you act with w, and acting with w tells me that it's going to be w nu partial nu, like that, and this one is going to be, I'll write it here, this one is going to be v mu, or v nu if you want, partial nu, w mu partial mu f. All right, so every term in here will actually result in two terms. Let's write them here using Leibniz rule. So it'd be v nu partial nu w mu, if you want to put a parenthesis here, partial mu f plus v nu w mu partial mu f. Right? And this one we'll have with minus signs, we'll have w nu partial nu v mu, maybe let's write it like this, partial mu f, then minus the other one, which is W nu V mu partial nu partial mu f. Now, luckily, we're talking about smooth functions. This one cancels this one. And all that I'm left with is the following. Let's write it. V nu partial nu W mu minus W nu partial nu V mu. And this thing acts on partial mu F. All right, so nice. We found the Lie derivative of W with respect to V acting on F. Now, of course, we can remove the F, right? Because this is true for all F's. And then we found exactly what this thing is. In the coordinate basis, in fact, I'm going to write it here. I'm going to write here. In a coordinate basis, LVW, right, it's equal to, and I wrote here, V nu partial nu W mu minus W nu partial nu V mu partial mu. These are the elements of the basis, right? These are the components. Now, do you remember what these components are? We did an exercise in the video about vectors, computing the components of the Lie bracket of the commutator of the two vector fields. This thing right here is indeed the components of the commutator of V and W, right? This is the component mu. Wonderful. So what does that mean? Well, that means that indeed the Lie derivative of a vector field, let me just erase this and give the result, is just the commutator of the Lie bracket between V and W, which of course in a coordinate basis is given by this, as we computed in the previous video. You see how we computed this? Knowing once you know the one for a scalar, you can upgrade it the one for a vector field. And you can keep doing the same for higher order tensors. Let's do it for one forms. All right, let's compute the Lie derivative in the direction of V of the one form sigma. That should be easy if we use a trick similar to what we did before. Let's put sigma into things that we already know how to compute the derivative. For example, I get here the contraction between sigma and a vector x, an auxiliary vector x, which is of course the contraction, the components. The contraction can be computed in terms of the components as follows, as we know. Now, the Lie derivative in the direction of V of this is a function, because these are vector fields, right? Vector fields and one-form fields, so the scalar that you get contracting them is a function. And this is the Lie derivative of a function, so I can write it because I know what the Lie derivative of a function is in a coordinate basis, and that's what I wrote here. And then I can also use Leibniz rule. Leibniz rule tells me that this is going to be the contraction of sigma with the Lie derivative of x in the direction of V, plus the Lie derivative of sigma contracted with x. Okay, so this one I know, because the Lie derivative of a vector, I know what it is. The Lie derivative of a vector is the components are these ones. The component super mu is this one. Okay, so I get this and I contract it with sigma mu. So I get these two terms, sigma mu contracted with this minus this, which is the components of the Lie derivative of the vector x in the direction of V. And finally, I get the one that contains the only thing that I don't know, which is what I want to know, the Lie derivative of sigma with respect to V. Okie dokie, what we're gonna do now is use Leibniz rule to expand this derivative, so like this. And then we realize that this term and this term are actually the same, aren't they? You can tell this if you swap the mu by a nu and the mu and the nu by a mu, it's exactly the same term. So let's just swap this one. It's a sum, right? It's a summand. I can do it. It's dummy indices, so let's do it. All right, and then we can cancel this and that. Wonderful. So now I can put this on the left-hand side and leave this one isolated. For simplicity, let me just rewrite this in an easier way as the components of what I'm looking for, the Lie derivative with respect to V of the form, say the one form sigma, component sub nu x super nu, right? This is the contraction of this one form with this vector. Wonderful. So all that we need to do now is put this on the left hand side and everything else on the right hand side. So I can write here Lie derivative direction of V of sigma component sub nu contracted with x super nu. It's equal to, now I have one term here, so okay, I'm gonna write first V mu partial mu sigma nu, and this is contracted with x nu. And then the other term is this one that goes to the other side with a plus, and I'm gonna write it here as well, sigma mu partial nu v mu contracted with x nu. Ha! How nice! So, the lead derivative in the direction of v of sigma component nu, of course, it's equal to v mu partial mu sigma nu plus sigma mu partial nu v mu. Because this is true for all x is an arbitrary vector, an auxiliary vector that I used. All right, I can write it here, then in a coordinate basis. I'm going to write it directly in a coordinate basis.
In a coordinate basis. So this is v mu partial mu sigma nu plus sigma mu partial nu v mu.
Contracted with the elements of the basis, of course, dx nu. All right, there you go. So this is the lead derivative of one form. You can keep going. Now you can do any kind of tensor that you want, like a 1-1 tensor, a 2-0 tensor, etc., a 2-form. Actually, yeah, let's leave it as an exercise. As an exercise, prove that the lead derivative of a 2-form is given by this. This is just grinding a little bit using the same kind of techniques that we use to compute all of them, from the function to the vectors to the one-forms. Now do it with 2 forms, and so on and so forth. We can obtain expressions for any arbitrary tensor. As you can tell, it gets more complicated as we go. All right, one more thing about the lead derivative. Let me give you an identity that is considering, it's even called magic and things like that. I don't like calling it magical or magic or anything. Is the Cartan identity. The Cartan identity tells me the following. The Cartan identity for n forms tells me that the lead derivative with respect to the flow of v for n forms, I can write as take first the exterior derivative, then contract with the vector v, plus take the exterior derivative of doing the contraction with the vector v first. This Cartan identity is kind of fun to test. I recommend, if you want to practice a little bit, test that is satisfied for 1 forms and 2 forms. When you do that, you'll get 2 things. You'll get bored and you'll get like super muscles for index notation and calculations like this. All right, this is it for this video. I hope that you enjoyed it as much as you could. I hope that you learned some things. I know that this could be very abstract math for people who are not familiar with the language. So please, don't be hesitant at all to ask questions in our Friday sessions. I will see you in the next video to talk about the notion of covariant derivative, connection, preparing the way for the notion of parallel transport and curvature that will come later. In any case, I will see you then, and until then, take care.